Okay, so thank you to Jurek for organizing this conference and for giving me the chance to talk here. So we'll talk about area law as a distiller of classical geometries in quantum gravity, in particular in the framework of loop quantum gravity. And this work in collaboration with Alyosha Amma, Janet Hung, and Minhee Zhang. So let me go to the summary. So first I will spell out some words about quantum entanglement and talk about its quantification and measurement. Then I will spell some words about the area law as a distiller of classical geometries, so as a way to discern amongst different possibilities in the quantum theory. Then I will talk more about entanglement and about a way to look at the complexity in the entanglement and other issues such as thermalization. Then I will switch on the main part of the talk, which is about the recovering of this state in low quantum gravity that fulfill this asymptotic limit and encode the area law, and a way to recover some current state which can work in this way. Then, well, if I will have time, I will show some details about this derivation, and then we talk about the way in which we can forbid space-time Schrödinger cats to arise in the theory. So let me first say, so we can take into account a system which is B and the subsystem which is A, and the reduced density metric will be obtained by tracing out the degrees of freedom which are outside of A in B minus A complement. So this is the reduced density matrix with respect to subsystem B. And we can define the entanglement entropy for Neumann in terms of minus the trace with respect to the degrees of freedom in subsystem A of the reduced density matrix log rho. So a simple example about that may come from considering a system with, for instance, the spin. And we take into account the four bases, and now we compute the reduced density matrix by tracing out the degrees of freedom that concern to the spin 2. So we can see that, I mean, for spins that are along the same direction, this will give us a reduced entanglement entropy, which is 0. But for instance, if we take into account other states, for instance, such as the APR state, we'll have a maximum entropy. So we have logarithm 2. So the reduced density matrix here looks like that one of a mixed states, and this is a feature that come many other times into account. For instance, if we consider a system in which we have a Rindler observer which is accelerating along, for instance, the x-axis with an acceleration 1 over r. So if we trace the degrees of freedom here, which corresponds to the positive part of the axis, we will discover that the accelerator of the observer, see the vacuum as a thermal mixed state. So these are all properties that we will come back later on. Let me still introduce some more details for the analysis that is about to come. It is about the Eigen entropy, which is a different way to characterize a set of distribution of probabilities, and is more connected actually to observation because it involves momenta power n of the probability distribution of the reduced density matrix. And so, for instance, n equal 2 is linked in this way to the purity of a state. You can see that there is an n dependence, and this n dependence is actually interesting in the sense that if we, so this way of dealing with the entropy, with the Rayleigh entropy, is easier in the sense that calculations are easier to be performed, and we can analytically continuate toward the limit n2 equal 1, and then recover again the von Neumann entropy, the entanglement entropy. So the limit n equal 1 is exactly the entanglement entropy we were showing before. Furthermore, they show some other properties. That is the fact that the Renyi entropies decrease as n increase. So the maximum entropy is the entanglement entropy here in these families, one-parameter families of entropies. So let me say something else. That is, this entanglement entropy show also strong subadditivity. And so if we individuate a tripartition of a system, we can actually see that the sum of the entanglement entropy for the subsystem A plus B plus B plus C is actually bigger equal that is sum here. So this is general as mathematical property, but let me go now a little bit more into some situation in physics. And from now on, I will go forth and back between quantum gravity and condensed matter systems. And we'll see there's many analogies, and actually we'll try to push forward this analogy as much as possible. So there has been some study quite recent by Sentil and Zwingli, and these people have been succeeded in finding some universal crossover function between the entanglement entropy and low temperature thermal entropy in some quantum many-body systems which are gapless. So this is one of the features that actually give us the possibility to connect some finite temperature system, okay, and then cause the thermal entropies there in some large limit, which is here for large size of the system, of the boundary of the system inside the system. And indeed, for the ground state of local Hamiltonians, we can see that the entropy is actually dominated by a term which is proportional to the area. Then, depending on the system, particular system that we are considering, we can have some other correction which can go with the logarithm of the area, depending on some central conformal charge. So here, let me go a little bit more into the part of the talk that concern the area law and a way of using it as a distiller of gravity, gravitational geometries, and which is the link between the two. Well, we know that for black hole, the Bekenstein-Hawking formula holds, and we know that there have been many attempts from the past to recollect this black hole entropy actually to an entanglement entropy. So the very first attempt is quite old, since it traces back to Sorkin 83. It's actually a paper that had been posted a few months ago, but it was talking about this many years ago. So then, some other paper by Sorkin and collaborator Bombelli, Cowell, and Lee appeared, and Shrenichky and Frolov, Novikov, Jacobson, Saskin. So it will be very long to have a complete list here of people who have been working on this idea. Another point is that matter can actually enter some renormalization of the entanglement entropy through the normalization of the basic constant in the theory. And let me see that quite well recently, let's say in the last decade, from the Ryu Takanagi proposal, there have been also an attempt to connect entanglement entropy to holography. And in particular, entanglement entropy in a conformal field theory in the dimension has been linked to the minimal surface in anti-de Sitter T+1 dimensional through the Ryu Takanagi formula that was recently proved by Lekvovitz and Baldacina. But besides that, there are many analogies between gravity and spin system, and this has been highlighted actually by many people, let's say also Beloku, and before him many others, of course, which is about the fact that, these are systems that may also, so first of all, the systems that have, from a classical point of view, a heat capacity which is negative. So also many condensed matter systems have this heat capacity which is negative. But also the spin system that have this negative heat capacity also shows many times long range interactions. And let me say that entanglement entropy of ground state of local Hamiltonian shows the area law in spin system, and this is, has been quite strongly established. So, so for non-equilibrium thermodynamical classical matter, so there has been this discovery of the negative capacity, which is something that traces back to the gravothermal catastrophe by Antonson and discussed by Lyndon Bell and Wood back in the days. And the presence of long-range interaction for some classical, before some classical thermodynamic to break, and this is this encodes, this manifest in the fact that energy and entropy are no more extensive, and there is an inequivalence of microcanonical and canonical ensembles, and there is a relaxation toward thermodynamic equilibrium. So this is typical not only of the some condensed matter system, but also of gravity, has been highlighted so far. So the fact that black hole have negative capacity has gravitational gas has been highlighted as well back in the days by many people. Let me say that there have been also some other studies showing that if we look at some spherical shell, okay, of gas and some symmetrical distribution, we see that as far as the gravitational interaction are not important, the entropy scale like the entropy of the volume. But as soon as gravitational interaction, self-interaction becomes more important, then the entropy is no more volume scaling. And actually, when the boundary of the system approaches even horizon, now there is a behavior which scale likes the area. So, and these scaling laws of the system are exactly, so identical to those one of black hole, okay, but without actually being there real even horizon. So, and well, I may say more about connection with Ising models, but let me go more into some, switch back to some details of entanglement entropy again. So let me say first that in order to characterize the complexity of entanglement, there are techniques that are going to be developed here by here with a very high rate of frequency by people working especially in condensed matter that are interested for a very peculiar reason, of course. And one of those is quite new. So we're actually talking about work by people, Schaffer, Chaman, Hamma, and Mucciolo, which is in the last 12 months, basically. So what happens is that you can characterize the complexity of entanglement entropy by looking at a ratio. Well, first, you have to order in a decreasing but also an increasing way. It is not important. The eigenvalues of the density matrix, and then you define the ratio of consecutive spacing of these eigenvalues, and then you plot them. Okay, then you see the distribution that they have, and it seems, well, the study that have been done until now show that there are basically three distributions. So there is a Poisson, a Wigner-Dyson, and another intermediate distribution that originate, and we can conclude then something about looking at the distribution of this spacing of this ratio of consecutive spacing, because for sure if we have a Wigner-Dyson distribution, so we have talking about something which is like random matrices, so there is a thermality, okay, for this entanglement entropy that we are looking at. So the issue here is see which are the thermal properties, and another issue could be also to look as a state can evolve toward a Gibbs state, so toward a thermal state, and this is for everyone that love of course coffee, this is a serious issue because thermalization is quite important, and it's something that indeed many people have been thinking about back in the day. So there is I will mention in a while the Eigen State thermalization hypothesis by Sternitsky. Let me say here that if you consider some closed quantum system and a pure state in it, okay, and that this is not thermal. So there is a way in which we can recover still a thermal state through the Eigen State thermalization hypothesis that I'm going to talk about in a while, which is basically the possibility that we can have thermalization on the boundary, okay? So this is exactly this Eigen State thermalization hypothesis. This is a statement about thermalization. So we have a state psi, but what is important is that this is a state that has some high energy. So high energy with respect, of course, to the evolution equation, kind of Schrödinger equation that we have. But the Schrödinger equation from the system, I'm going to show in a while, will impose a peculiar condition here. So I will be back in the next slide. So here we consider a state, and we consider its reduced density matrix. And if this property is true for local observer in the subsystem A, so this, which is a statement about the thermality of the state, you can see that, I mean, thermalization then was already included in at the kinematical level in the Eigen State. And there is also a way to encode the relaxation toward thermal state here. The temperature of this thermal state is actually related to expectation value of the Hamiltonian through this reduced density matrix, which is actually which has a Gibbs state behavior. So, but unfortunately, this is not the case that we're considering this theoretical framework that I'm going to discuss here today, which is low quantum gravity, because the state in low quantum gravity must be annihilated by the scalar Hamiltonian. That means that, I mean, the state of the physical Hilbert space must have energy zero, so to say. So we cannot apply the eigenstate thermalization hypothesis here. So how we can look at thermality and thermalization? So that's why this characterization in terms of this distribution of the ratio of the spacing of the eigenvalues of the energy density is important. This is indeed work in progress that we're doing with Alyosha Ham and Janet Hung. So let me go now to low quantum gravity. So, and what we are considering here is a system, okay, in which the states are characterized by a triplet. So we have a graph, which is a collection of L-oriented links and nodes, and then we have some assignments of unit reducible representation of a group element, which is SU2, to the links, and of SU2 intertwiner at each node. Okay, so these are the states. I'm not going here to introduce more than that low quantum gravity, because it would take too much time. But let's say that the states are this one, this spin network state. Okay, a graph, color graph. Okay, and let's say that, I mean, the spin J representation are isomorphic to SL2C representation, because there is a way to select those among the SL2C through some linear simplicity constraint, which is a way in which we extract gravity from out of topological theories that are used in order to perform covariant quantization that after discretize a spin form. So let's say that the theory is consistent now with this assignment and with this restriction on the J representation. The meaning of this spin network state, the meaning that they can have, well, it's still a matter of study for a certain sense, but let's say that the way in which we're going to interpret here, you know, and what is follows, so if you have to have a picture in mind, is through correspondence to quantum 3 geometries, and especially to twisted geometry. So there is work that have been done in the past few years by Laurent Fredel and Simone Speziale about that. So basically, the state that I will consider are states that actually will be picked around certain geometries, and they will be picked through the imposition of the representation to be picked around the expectation value of the area operator, and thank you, and there will be a phase that will be picked around the dihedral angle, which is the discretized version of the curvature in the Regge discretization of gravity. So let's say that here you look toward discretized Rage gravity. So, so now we want to see what can entanglement entropy say us, okay, about recovering a classical geometry, and we are going to encode the area load, okay, for the ground states, saving gauge invariance, and also imposing this non-appearance of microscopic quantum superposition for the state of geometry. And these are the states that we've been going to use in certain points, since we want to pick our geometries around semi-classical geometry in some limit, which is a scaling limit for the georepresentation that obviously that we're going to use. Okay, so the way in which we're going to, so this is the area law that we're going to actually find, and you can see that there is a log correction that come out of the calculation. So this is the calculation for the many-body problem. Okay, so we're going to distinguish amongst one body problem and many-body problem. And one body problem actually is going to be distinguished in one links and main links. Okay, so one body means that the region around which I'm tracing has one node inside. Okay, so it can be only one link, or can be more links protruding out of this node. The way in which I select the state not to have space-time Schrödinger cats is by imposing that the Newton information as large distances which are disconnected is 0. So this quantity, which is written in terms of the entropy, any entropy order 2, which is then the purity, must be 0. So the state then that we can recover give us a prescription to go for new coherent state to pick our quantum state around certain semi-classical geometries. And these are characterized by the same expectation value as the one that were considered before, but they're faster, in the sense that, when the area increase, this converge faster toward semi-classical expectation value of this area and the Wilson loop operator. And they actually work because they fulfill the resolution of the identity. So let me switch back again to equivalence with the condensed matter system and show that we can indeed have a lot of analogies. So this is a system that has been KIDEV model, a model which has been studied for quantum computation. So the graph here has orientation plus minus, and there's qubits on the edges there are, and vertices and plaquettes, and this is the Hamiltonian. And we are labeling everything with respect to a discrete group G. We have an Hilbert space, okay, of functional on these discrete groups with a normal basis for the qubits labeled by the discrete groups, which has dimension D. And the operator we can define here are actually operated by multiplication left and right by this group element in the state, and another operator that superimpose a delta for a group element on another H group element. And we can construct gauge transformations out of that. So at the vertices, multiply along the links which flows into a vertex for these L operators, and this gives rise to the star operator. And then the plaquette operator, okay, which take into account multiplication of this T operator along one plaquette, okay. So, yeah, thank you. So these operators commute, and then we can easily find the nilpotent state that satisfy, minimize the Hamiltonian. And these are the family of ground states that we have discovered here. So this would be kind of like solving the scalar constraint here in loop quantum gravity, which of course is not a trivial task. But look at, what we have here is that the reduced density matrix is unitarily equivalent to a matrix that only addresses now the degrees of freedom which are at the border. And that entanglement, okay, is an area law, and only because indeed, degrees of freedom are constrained by a global constraint ought to be that one on the boundary. But what we have not done, and what could be the opportunity, is also to find bounds on the value of the entanglement entropy, which are computed indeed in the KIDEV model. So they have the possibility of extracting more and more information about the system. So let me say something about this Bisogniano-Wichmann state. So this is a state that had been introduced in the literature by Bianchi Myers, Kirko Rovelli in the recent papers to look at the thermality. And this can be actually a state good, I mean, to study the issue of thermalization. What is this Bisogniano-Wichmann properties? Basically, for state, which can be only one link state, we're going to trace around the target indices, okay? And we're going to find the reduced density matrix, and this is exponential to the boost operator. So this boost operator, I mean, you have to remember that through the simplicity constraints, it's related to the rotation operator. But what is important here is that naively we would think that this state has the area law, but it doesn't. What we could check through those analysis of the distribution of the spacing of the eigenvalues is that has some thermal properties, okay, which indeed were the one that the authors claimed. But naively we would expect it to give the area law, but not. So that's why we went back and we considered one link state, and we were imposing, choosing a particular base that diagonalizes the action of functional of rotation operator and boost operator. And then, I mean, we were imposing this area law and then finding the state, okay, that must have this barrier law. So you can see that, I mean, it's a deformation of the state that were considered before, but now with this enveloping algebra modification indeed, which is the one that provides this. So here there's some details about the calculation that I may have the time to talk about, right? Since I still have 5 time, right? 5 minutes.
No, because there is a question time. There are some people who want to ask you some questions.
And then, I mean, they can ask question later on, no?
Not really, because
okay, well.
want to listen to answers.
Okay, so it's Jurek is right. So I'm going to skip this, okay, and this. But no, let me skip this, please. Okay, thank you very much. Okay, so it's, as I was saying, so we have this state that we were recovering before. So we can prove that indeed in the asymptotic limit, which is this limit in which we're scaling the J, okay, the assignment on the links of the spin networks, and we look, I mean, at the saddle point approximation of the main part of the entanglement entropy defined in the von Neumann way, gives indeed, I mean, this one, which is 1/4 the expectation value on the state of the area operator in a quantum gravity. So that was for one body, one link, but we can have one body, many links, okay? And the analysis still goes the same way, just picking this around state, which has this deformation now to encode the area law that we were finding in for one link state. And this is the result that we find for the area law. Well, you can see this is the Gaussian distribution, okay, for peaking around this J, okay, which is more or less 1 of square root of the area. The many bodies can also be obtained, but to obtain it we have to go to quasi-adiabatic continuation here, okay? That is something again that we borrow from tools developed in many body quantum system in condensed matter. And so basically what we do, we consider some local Hamiltonians. So here for local Hamiltonians I'm using some jargon, which is in condensed matter physics. These are made out of operators which are supported on only subgraph, okay, of the initial graph gamma or x that I'm considering, and then consider some convolution and this adiabatic operator, and then I can indeed change the graph but not change the result, and I can also impose, okay, that the mutual information goes to 0 in such a way that I can be safe about the fact that state with Schrödinger-Katz superposition are ruled out in this theory or are not considered in the physical hyperspace of the theory. So that, I mean, my classical limit will be meaningful. Going to conclusion, so we're talking about entanglement entropy, and even a new way of addressing thermality of the state and thermalization. So this is work in progress and is quite new, so to say, even in the condensed matter communities that is developing those tools. But the main part, I would say, of this talk is this conjecture. So let me say that the area law is something that we should encode so it's not mine, of course, has been conjectured and discussed from a long time, but there's many hints that suggest that the area law could be a stealer of semi-classical geometry. So it's the point is that can we use that then to analyze some theories of quantum gravity? And we have applied all this tool and machinery, indeed, not to a particular theoretical framework, which seems to be very analog and very close to some condensed matter models. So there are some questions, of course there's many questions left open, and one is if there is a relation between this Hamiltonian constraint, the entanglement entropy, and the Einstein then equation. So this is because actually the adiabatic mechanism, the adiabatic operator that was of continuation that I was showing before, is connected, can be connected to the local Hamiltonian for this system. Yeah, so this has also consequences, as I was mentioning, the level of the modification of the coherent state, and then the level of extracting semi-classical geometries in this series. Okay, so thank you.
Okay, thank you. Questions? And a question?
I'm missing the connection with black holes, because it seems that you are sort of, you discussed this black hole thing, but then you are discussing
the connection black hole is that we want to take into account the area law as something that is more general than only for so we want to argue using several arguments that have been pushed forward in the last years, that the area law should be actually something that should take into account not only system with an even horizon or but it's
you mean the
more general.
area law for the entanglement entropy?
Yes.
But that's okay.
But even for the entropy, because the entropy that for instance so this result here that I was mentioning before, where is that? Yeah, this is by Oppenheim. So what he was considering here is just a classical entropy of a system. So it's not, it's what he's doing there is first, it's just using the relation between entropy, internal energy of a system, okay, and temperature, and just writing a certain metric for a shell, spherical shell of matter, and just looking at the the discontinuity relation between extrinsic curvature, intrinsic geometry, and energy density. Okay, so to extract this, this relation for the internal energy, and then plotting, the behavior for the
I understand.
Entropy.
No, there is this one general problem with entanglement entropy, that it's cutoff sensitive. You know that, right? So therefore, that creates some questions whether it's a because it depends on the number of species and this kind of stuff, right?
Yeah. So so here in this framework, this is something that yet we are not going to observe, but it's something that we would like to look at. But where there will be also a more solid proposal also to encode other degrees of freedom, such as matter. So it's one of the problems in this model, in this theoretical framework, is that matter has not been coupled yet in a way which has reached an enough consensus. But this is one of the to-do lists that we have in mind. Yeah.
Okay.
It's an interesting question, in my opinion, also to think about what happened to falling information, because it could be really interesting to for example, discuss chaotic propagation inside, because I expecting that you have a semi-classical geometry, right? And then you are just in falling toward the full quantum region, but in the middle you have somehow an effective geometry. This is not completely smooth. So I expected that the information is scattered somehow back and forth in the geometry. Actually I have a short preprint about these aspects. Maybe it could be
Sure, we can discuss
interesting
about
to
that.
discuss.
So let me just say that you're right. So this is a very, very important, interesting issue. And indeed, these people, Terno and Levine, they have been studying actually entanglement entropy back in the days. I mean, where they were concentrating on other features, but they were actually interested from this point of view. And now, I mean, to be honest, I don't remember what they were concluding, but we can go through this again together.
Okay, we can discuss, of
Okay.
course.
No. No.
So the Rényi entropy is, well, let's say it's for many reasons. So you need the Rényi entropy if you want to encode that the modal information goes to 0, no, at macroscopic region. But it's mainly a trick. So we're going to use the replica trick, because the needed continuation for n to go to 1 of the Rényi entropy is the von Neumann entropy. That's the main reason I would say that. I mean, all the calculation that so it's, for instance, you can see from here, okay, that we are actually introducing this replica trick, okay. So that's we have been calculated things with the momentum n of the energy density, and then we extract the n to 1 limit. Yeah, that's the only way, because otherwise these elements of the energy density matrix are very long. Okay, I go. I finish.
Okay, thank you very much. Thanks, Julia.